In this objective, we'll discuss several applications of logarithmic functions to everyday life, including science and physical applications. A common application of logarithmic functions involves things that are measured on a logarithmic scale. And before I talk about that anymore, let's first motivate why we might think about something on a logarithmic scale. And simply, it's because humans are bad at understanding really big and really small numbers. So, for example, I have a couple of sets of numbers here, and let's try to select the bigger number. So I have in A, 2 different decimals here, and to compare and find the biggest number, it's kind of tricky. I essentially have to count how many zeros are here. 1, 2, 3, 4, and 1, 2, 3, 4, and I'll say, okay, these actually have the same number of zeros, and that tells me that then they're the same magnitude, so then this one would be the bigger number. But I really have to count those numbers to see. Similarly, in B, especially since there's no comments in this number, it's hard to see which one's bigger, and we really have to count these zeros. There's 1, 2, 3, 4, 5, 6, 7, 8 zeros there. 1, 2, 3, 4, 5, 6, only 7 zeros there. So 64 with 8 zeros is going to be bigger than an 83 with 7 zeros. And so it's really not the 64 or the 83 part that I'm comparing. It's really the magnitude of this number, how many zeros are there. Okay, in C and D, we have 2 examples that are written in scientific notation. So 3.4 times 10 to the 18th and 6.2 times 10 to the 16th. And because it's in scientific notation, I can tell right away that this 10 to the 18th part is going to end up with a bigger number than the part with the 10 to the 16th. So this is my bigger number. And in that last comparison, if I pick the bigger one, I have one number that is times 10 to the negative 100th and another number that's times 10 to the negative 20th. Well, that's like dividing by 10 to the 100th and dividing by 10 to the 20th. So they're both really, really tiny numbers, but this one's going to be the bigger number because I'm dividing by fewer copies of 10. When it's written in this scientific notation, I'm essentially just comparing the power on the 10 rather than comparing the entire number itself. And that's really where the idea of logarithmic scales come in. When the magnitude of numbers vary greatly, it's easier not to compare the numbers themselves, but to instead compare the magnitude of the numbers, like what we saw in C and D. In some situations, instead of caring about the actual value of a number, we care more about the exponent when it's written in scientific notation. Since logs tell us about powers, thinking like this is called a logarithmic scale. So we're thinking on a scale in which logarithms are used in the measurement of quantities rather than the value of the quantity itself. We'll discuss 3 different examples of measurements that are measured on a logarithmic scale. The first that we'll discuss is pH. pH is a really common measurement in chemistry, and it measures the concentration of hydrogen ions. Here we see some concentrations for some common everyday items, and the first thing that I notice here is that these concentrations are really, really small numbers. They're decimals less than 1 because, well, a concentration is a proportion, and so it should be less than 1. And it is a little bit difficult to compare these. If I'm looking at orange juice to coffee, it's hard to tell how much more hydrogen is in orange juice than in coffee because there's just so many decimals going on, and my brain is not very good at thinking about numbers that are so incredibly small. What we could do instead is think about the log of these numbers. So I'm going to pull up a calculator real quick. The log of the concentration of hydrogen in blood would be log of 0.000. Even goodness, this is hard to do. There are 7 zeros there. 398107117. My goodness. Okay. And we get about negative 7.4. And we can do this for all of these concentrations. Now, all of a sudden, I have numbers that are a lot easier to compare because they're in the range of numbers that I like to think about. Numbers like 3 and 11 and 7.4. Maybe what's tricky about these is that they're negative. And so what we tend to do is think about the opposite of the log of concentration. So if we typed in the opposite, the negative of the log of the concentration, that's what we're going to call actually the pH. So we'd get 7.4, 5.2, 11, 3.7, and 7. And we actually see that formula written another way down here. By defining the pH as the opposite of the log of the concentration of hydrogen ions, we get numbers that are a lot easier to compare. I can immediately tell that ammonia has a larger pH than all of the others, and that the smallest pH is orange juice. And I see that water and blood actually have a very similar pH. There is one thing that we have to be very, very careful about, and to highlight it, we'll compare ammonia and water. The pH of water is 7 and the pH of ammonia is 11, and that difference is 4. So it's tempting to think that the concentration of their hydrogen ions differ by 4. But it doesn't quite work that way because we're working with a logarithmic scale. If we compare the original concentrations of hydrogen ions for ammonia and for water, we see that these numbers vary by a factor of 10,000. We have to multiply the concentration of hydrogen ions in ammonia by 10,000 in order to get the concentration in water. To be able to see that difference from the pH of 7 and 11, we actually will need to think about this difference of 4 being on a power of 10, and that gives me my difference of 10,000. So in that way, the pH scale gives numbers easier for our human brains to understand, as long as we remember that if the pH of two quantities differ by 1, their concentrations actually differ by 10. If the pH of two quantities differ by 3, then their concentrations actually differ by 1,000, or 10 to the third power. We'll try one example of this. So seawater has a pH of 8.74, and we want to know the concentration of hydrogen ions in seawater. And we'll use that formula, pH equals negative log of the concentration of hydrogen ions. So if the pH is 8.74, we can go ahead and plug that in. And then to solve for the H+, this is essentially solving a logarithmic equation. I need to isolate my logarithm by dividing by -1. And then I can convert this to an exponential equation like this. We might leave the concentration in this form, 10 to the negative 8.74, or we could put this in the calculator to get an approximation. Another common measurement that is actually a logarithmic scale is the Richter scale, which is used to measure the intensity of earthquakes. Let me tell you a little bit of science before we talk about the logarithmic scale going on here. So an earthquake is measured by a seismograph, and a seismograph is pictured here on the right, and it's a device that can record the intensity of an earthquake. A seismograph is essentially a pin at the bottom of a heavy weight, and when there's an earthquake and the earth shakes, the weight will shake and it will scratch out kind of this wavy line on the paper here. And what we actually measure to decide how intense an earthquake was is how far out from the middle these lines go. So what is kind of the distance from, if the ball had not moved at all, what is the furthest distance out that wave kind of moved? So this is how we typically measure these, but the thing is that some earthquakes barely make a dent. Some earthquakes might have kind of a seismograph that looks like this, while others might have a seismograph that looks like this. And that distance that the ball moves is actually quite different between those. The devices are so sensitive that we actually measure these in microns, which is 1/1000th of a millimeter. So it's super tiny and super precise. And the distances can vary dramatically. Each seismograph is actually a little bit different. So each seismograph actually has its own kind of base threshold that we call I sub 0. And when we measure an earthquake on a specific seismograph, we actually measure the intensity as a multiple of that I sub 0. When there was an earthquake in Tennessee in 2018, don't know if you remember that, but it was about 25,000 times than the baseline amount for the seismographs here. The Nepal earthquake was about 63 million times more intense. Whereas the 2004 earthquake in the Indian Ocean that caused a tsunami was about 1.9 billion times more intense. And what we're seeing here is that we have numbers that vary dramatically. We have 25,000 times and we have almost 2 billion times. That's a huge range of numbers that we might be comparing, 25,000 up to 2 billion. And whenever we have numbers that are varying dramatically, it's a good time to use a logarithmic scale. Here's how it works for earthquakes. The magnitude, m, of an earthquake is defined as the log of its intensity divided by that baseline intensity, I sub 0. So let's calculate the magnitude for some of these. For the 2004 Indian Ocean earthquake, if I take the log of this intensity, this whole thing here is my intensity, and if I take the intensity divided by I naught, and I want to take the log of that, I'm essentially taking the log of this 1.9 billion number, and if I put that in a calculator, I get about 9.3. If I do that for this last one, just as another example, so my formula would be that the log of the intensity divided by I naught. When I do that, the I naughts actually cancel out, and I'm really just looking at the log of 25,119. And if you throw that in a calculator, we're going to get 4.4. I'll go ahead and fill out the other ones, but you can pause the video and calculate these as well, just to make sure you're understanding what's going on here. By computing the logarithm of the intensities, rather than just comparing the intensities themselves, I now have numbers that are a lot easier to compare. I can see that the Indian Ocean and the nuclear disaster earthquake were about the same-ish, and the East Tennessee earthquake was a lot smaller. But because this is a logarithmic scale, we do have to take these with a grain of salt. And remember, for example, just because these are off by about 2 doesn't mean that the Fukushima nuclear disaster earthquake was about 2 times worse than the Haiti earthquake. It actually means that it was 10 to the second, or really 10 to the 2.1, which is a little over 100 times worse. We'll use a similar train of thought to compare the intensities of a 5.2 earthquake and a 6.7 earthquake. Right away, we can see that the magnitudes differ by 6.7 minus 5.2, or 1.5 on the Richter scale. But this does not mean that one was 1.5 times worse than the other. Instead, one was 10 to the 1.5 times worse, or about 32 times worse than the other. Keep this in mind the next time there's a big earthquake and people in the news are comparing it to another one. An increase of one number on the Richter scale actually means an increase of 10 times worse. And an increase of 3 on the Richter scale means an increase of 10 to the 3rd times worse.